In the previous video, we discussed the analysis of T sections. In this example, we will see how to execute those procedures that we discussed. So this is example 4-5, analysis of T sections in positive and negative bending region. So we will analyze T section, the beam, one in the positive bending moment region and another in the negative bending moment region, and see how the two analysis procedures differ. Now, this is a part of a continuous flow system given to you. It is, these lines are showing continuity on all four directions. These are four columns, and these dashed lines are representing the beams running between these columns, and this is the floor beam resting on these girders. So we are going to have analysis for this floor beam, central floor beam, at two different locations, AA, which is at midspan, and BB, which is at the support at the negative bending moment region. Now these are the dimensions: 10 feet on this side, and this is 24 feet center to center of the columns. Slab thickness is given as 5 inch. Now we are the first part of the problem. These section lines AA and BB, and these are the sections. This is section AA and this is section BB. So look at the difference between section AA and section BB. This is the positive bending moment region section. So we have, compression at the top, tension at the bottom. So this is the tensile reinforcement, and over here this is a negative bending moment region. So this is the tensile reinforcement, and this is the compression side. So before we go to the analysis at AA and BB, the first part that we need to discuss is how to calculate effective width BE for these sections. So essentially we will have same effective width for both of these sections. Look at this, because all the parameters, if you will see, are same for both sections. So let's see, because these are sections of one beam. I mean, these are different sections at different locations for the same beam. So let's see how we calculate. So the first part is to calculate effective width BE for the beam. So the first part of the problem is determine BE for a beam T section that is part of a continuous flow system. So we have discussed this, that the effective flange width BE is given by the least value out of these three for an interior beam, for a T beam. Alright, this is our case. This is only for an edge beam. This is for the interior beam. So we have, and we are discussing this beam, which is of course an interior beam. So these equations apply. So let me copy this down to our current page, and then we will see how to calculate. So these are the limits. So let us first figure out the parameters involved in these equations. So in our case, BW, we need to write this down. BW, in both cases we have BW of 12 inch. This is BW of 12 inch. So let's write this down. BW is 12 inch. Alright, what is that? The other parameter. The other parameter is SW, clear transverse span between webs. So clear transverse span, this is a web and this is another web of an adjacent beam. So clear transverse between these two. We need to look at this. This is 10 feet is center to center, and we need to know clear between these two webs. So that clear distance, we need to know the dimensions of these two beams. Let's assume this is also 12 inch wide beam, and this is also 12 inch wide beam. So if this is 1 feet wide, this is also 1 feet wide. So the clear distance between these two webs would be 10 feet minus 6 inch minus 6 inch. That would make 9 feet. So in our case, SW is 10 feet, 10 into 12 inches minus 12 inch. Or you could simply do it in feet first and then convert to inches. So 10 feet minus 1 foot, so 9 feet. All right, so then you can write down 9 into 12, that would make 108 inch. Now let's see what other parameter we need to know. SW has been calculated. HF is thickness of flange, and we know it is given as 5 inch. So HF is 5 inch. This was the thickness of the slab. And what next? We need to know LN, which is clear span of the beam we are discussing. LN is clear span of the beam, longitudinal clear span. This is longitudinal clear span of the beam from this end, from this edge to this edge. So the center to center is 24 feet, and let's assume that, again, let's assume that this, although we're not given this data, but let's assume that this is also 1 foot wide beam and this is also 1 foot wide beam. So the center to center is 24 feet, and the clear distance will be 24 feet minus half feet on this side, half feet on this side, so you will be getting 23 feet. So LN is 23 feet. 24 feet minus, half feet, half foot, and then half foot on the other side, so you get 23 feet, and that makes 23 into 12, that makes 276 inches. I think now all of these parameters are known. Let's just insert those values and calculate BE. So BE is, the least value of these three. Number one is BW plus 2 times SW by 2. So 2 times SW by 2. And then the second is BW plus 2 times 8 HF, 2 times 8 HF, and the third value is BW plus ln, 2 times ln by 8. Alright, so this would be giving us, let's put the values. So BW is 12, 2 times SW is 108, and you're getting the answer. So we have calculated these values after putting the values. So 128, 92, and 81. This is the, least answer over here is 81 inch. So this controls, this is the least value. So BE will be taken as 81 inch. So for all other calculations that we are going to see in future, we are going to use BE equal to 81 inch. 81 inch. So BE is 81 inch. So the first part of the problem is done. Now the second and third part, for these, for second and third parts, in fact, this was, general part for the first part that we did, but actually the problem is to calculate MN and phi MN for section A and section AA and section BB. So you need to calculate phi MN for this section and phi MN for this section. So this is the actual 2 parts of the problem. This was indeed a preliminary calculation that you need to perform. So for part 1, for both parts 1 and 2, you have same concrete, FC prime 4000 psi, because of course this is same beam running between two girders, so of course it is same concrete in it, FC prime 4000 psi, and same grade of the steel, FY 60 ksi. So this information is same for both sections. For section AA, this section AA, we need to calculate phi MN. So starting with this section AA, let's list down the properties of section AA. Let's take it down a bit deeper so we can avoid scrolling everything down, every time scrolling down. So let me see, where did we paste it? So now we have it available right here. So for this section AA, let's calculate first AS. AS would be, we have 6 number 7 bars. So AS is equal to 6 into area of each number 7 bar. Each number 7 has 0.6 inch square area. So 6 into 0.6 inch square, we're getting 0.36 inch square. So AS is this value, and we also have some reinforcement on the compression side. So we have some AS prime as well. So let's list down AS prime also. AS prime equal to, we have 2 number 8 bars, so 2 into in the area of 1 number 8 bar, which is 0.79 inch square. So AS prime becomes 1.58 inch square. So we have AS and AS prime, and next we need to look at D and D prime values as well as DT. So these 3 distances. So let's first look at DT. DT is distance from extreme compression fiber to the extreme layer of tension steel, to the centroid of extreme layer of tension steel. So we need to know some distances based on procedures that we have already discussed. Clear cover is 1.5 inch, and then we have a shear stirrup, and then we have half dia of this longitudinal bar. So those make up to about 2.5 inches. So D is H 24 inch minus distance from extreme tension fiber to the centroid of the first layer of extreme layer of tension steel. That is 1.5 inch clear cover minus dia of stirrup, full dia of stirrup bar, and that may be 3/8 inch or maybe 4/8 inch. Let's let's take it equal to maybe 3/8, or let's take it equal to half inch, 4/8 inch. So this you have to add this plus half dia of the longitudinal bar. The longitudinal bar is number 7 bar. So number 7 bar means 7/8 inch dia. So half of 7/8, let's take it approximately equal to 8/8 bar. We're just making an assumption, approximation on the conservative side, that we have although we have number 7 bar, so exact calculation would be like this: half dia of number 7. So number 7 is 7/8. All right. So this has been taken equal to, as approximately taken equal to half 8/8. Although this is number 7 bar, we are taking it approximately equal to 8/8 because not a big difference, and this is not going to make a big difference. So the final answer, this will become half. The final answer, this will become half. So half plus half would make 1, and 1.5 plus 1 would make 2.5. So this would become 24 minus 1.5 plus 0.5. This is dia of the stirrup bar, 0.5 inch, in fact 4/8, and then you add half inch as half dia of the longitudinal bar. So this becomes 24 minus 2.5, and then you can write down this is 21.5 inch. Sorry, this is DT. I mistakenly wrote it D. This is DT, where this is distance from extreme compression fiber to the centroid of the extreme layer of tension steel, this bottom layer of tension steel. All right. So DT, and then D value would be calculated. D value can be easily calculated if you add up some more distance. D value is distance from this extreme layer of tension steel, let me mark it down, this extreme layer of tension steel up to this level, centroid of tension steel. All right, so that distance can be calculated. You just need to add some more distance from the center of this bottom bar up to this level. So how can you add this distance? You need to know, one thing that you need to add is half dia of the bottom bar. All right, let's say 0.5 inch again, and then you need to add up half of the clear distance between these two layers of steel. So that would make, D would be equal to dt plus, sorry, not plus, minus, in fact, minus half dia of the longitudinal bar minus half clear cover between clear distance between two layers of tension steel. Now clear cover requirement, or the ACI requirement for clear cover between two layers of tension steel is that the minimum should be 1 inch. Let's assume this is minimum value 1 inch. So the answer for D will become dt minus 0.5 inch minus half of 1 inch. So that would become, now you can write down 21.5 minus 0.5 minus 0.5. So this becomes 20.5. 20.5 D value. Now the last thing that you need to know is D prime. So based on what we have discussed for the bottom, sorry, we are here for this section AA. So based on what we have discussed for the bottom bar, let me for the time being just script it down. So D prime is distance from this compression phase to the centroid of this compression reinforcement. Based on what we have discussed for the extreme layer of tension reinforcement, we can discuss, so 1.5 inch plus dia of the stirrup plus half dia of the longitudinal bar. You can again write down this would be 2.5 inch. So D prime is, so D prime is 2.5 inch. All right. So next we are going to use the procedure that we discussed for the analysis, and we have discussed that you can assume case 1, that is A, you can assume A equal to or less than HF, and then you can assume that the tension steel is yielding, so epsilon S equal to or greater than epsilon Y, and then you can calculate A based on those assumptions. And once you calculate A, you can compare, you can quickly check your assumption at step number 1, which you can see if your case was really case 1 or not. If it is really case 1, proceed and calculate epsilon S, compare it with epsilon Y. It should be, and most of the time this will be true, this will be a true assumption, and then you can simply calculate Mn. So let's quickly execute this procedure over here. We are assuming, so first assume that A is equal to or less than HF, so that means we are assuming case number 1. That means the depth, the equivalent rectangular stress block will lie completely in the flange. Second, we assume that epsilon S is equal to or greater than epsilon Y. We are assuming tension steel to be yielding. And then third, we will calculate A based on that assumption. So we will calculate A based on the assumption that tension steel is yielding. So ASFY divided by 0.85 FC prime BE. So now you can put in the values. So we have put in the values and found the value of A, which is 0.78 inch, and just note down we have put it we have put B equal to 81 inch, and this is the result that we have from those preliminary calculations. So based on this, the next step, is the fourth step is to check your assumption at this in the first number step. So your A value is 0.78 and HF was 5 inch. So A is definitely much lesser than HF. So this assumption is really true. So we have come to know that A equal to 0.78 inch is lesser than HF, which is 5 inch. So this assumption is okay, and you can proceed for calculating epsilon s. So the next step is calculate epsilon s based on a familiar equation that you know, d minus c divided by c into epsilon cu. So putting the values, before you put in the values, you need to know your c value. This c value will be calculated as a over beta 1, and beta 1 for fc prime equal to 4000 psi is 0.85, so 0.78 divided by 0.85, so you will be getting, so you get c equal to 0.92 inch. Next you need to calculate this epsilon s by putting the values. So let's put the values in the equation for epsilon s. This will become, d value is 20.5, c is 0.92, and then c is 0.92 multiplied by 0.003. So your answer would become, your answer is 0.0638, and of course the epsilon y value, epsilon s, is 0.0638, and of course this is greater than epsilon y, which is 0.00207 for grade 60. So your assumption of epsilon s equal to or greater than epsilon y is also true. So now just go ahead and calculate your mn. So mn is now simply calculated by the equation for under-reinforced sections, which is a is fy into d minus a by 2. In this case, since it was case 1, so when it is a case 1, the compression zone has constant width, uniform width. So it's the analysis process exactly similar to the process for rectangular cross section. So just put in the values. So by putting the values, you are getting this answer in kip inch, and then you can convert it to kip feet. So 362 kip feet is the answer for mn. Next we need to calculate phi. Now phi, if you remember, it depends upon whether the section is tension control, compression control, or transition section. In this case, the phi value, it depends upon epsilon t, in fact. So the epsilon t is dt minus c over dt into epsilon cu. Now of course, if epsilon s value is 0.0638, epsilon t value is in this case slightly even greater than epsilon s. So this will be definitely, this value is greater than 0.005. So this value is definitely going to be greater than epsilon than 0.005. So you need not calculate it. So this is greater than 0.005. You don't need to know the exact value. You just need to make sure where does it lie, where it lies in the definition for tension control, or the compression control, or the transition. So this is greater than 0.005. So phi value would be 0.9. So phi is 0.9. So now simply multiply in the final step phi and mn. So phi mn will be 0.9 into 362 kip feet. So you get the answer for phi mn, 326 kip feet. So this is your final answer, phi mn. This is exactly what we wanted to determine for this section, phi mn. Now you have seen that although we had some bars in the compression region, these two number 8 bars were in the compression region, and they are present, they are acting as compression reinforcement, but we haven't included them in our analysis. What is the reason? Look at the depth of neutral axis. The neutral axis is, at depth of 0.92 inch from 0.92 inch from this top surface, 0.92 from the extreme compression fiber, and this reinforcement is below neutral axis. It is at 2.5 inches from the top, so it lies below neutral axis. So although it was provided in the upper side of the beam, but the neutral axis is now so shallow, the depth of neutral axis is so less that this reinforcement is falling below neutral axis. It is falling in the tensile region, and if you want to incorporate the presence of this reinforcement, you have to consider it as a tensile reinforcement. But here is the point: why would you like to, now should you include this in your analysis or not? You should not include. Why? Even if you try to include it, though it is in the tension region, and you want to contribute to account for its contribution in the moment capacity as a tensile reinforcement, the epsilon's value at the level of compression reinforcement would be, that would be, if you try to calculate it, it would be epsilon s prime equal to, c minus d prime over c into epsilon cu. This is how you have been calculating epsilon s prime. Let me just show you how you have been, where we first discussed this formula. We had derived this formula from when we were discussing the analysis of doubly reinforced section. So you see this formula has been derived based on the consideration that this reinforcement would be acting as compression reinforcement, and the depth of neutral axis would be, the neutral axis would be lying below this reinforcement. So this would be really falling in the compression zone. So your answer for this, if your answer for this becomes positive. Why? Because c is greater than d prime, so you get a positive answer from numerator. So that's why you get a positive answer, and the positive answer here indicates that the strain value in the compression reinforcement is really a compressive reinforcement. So you get a positive value. Now here we can see, using the same formula, in this case c value is 0.92, d prime is 2.5. So then this is naturally a negative answer. So you see that c is 0.92, d prime is 2.5. So this is, numerator is a negative value. This is because the reinforcement is not actually a compressive reinforcement. This is actually a tensile reinforcement. So even if you try to calculate the magnitude will be equal to, so you end up a negative answer. And just look at the magnitude. It is greater than 0.00207, which is, it is greater than epsilon y. So this is yielding in tension. This is not acting in compression. So if you wanted to incorporate its effect in the calculation of bending moment, you could have included it by considering that now you would have two tensile forces, one acting at this level, at the level of d, and the other acting at this level, at the level of d prime. Both are tensile. If you just compare, if you just consider the diagram, the strain diagram, it would be probably looking like this. Let me show you. If this is, you will have, this is how the strain diagram would look like. This is very shallow distance of 0.92 inch, c value, depth of neutral axis, and this is the level of compression reinforcement, 2.5 inches, halfway between the compression, between the mid depth of the of the flange or the slab. We have compression reinforcement. Even the compression reinforcement, so-called compression reinforcement, because this is actually acting as a tensile reinforcement, it is lying below the neutral axis, and even this is yielding 0.005. Even this is yielding, and definitely this has to be yielding the tensile reinforcement at the level of tension reinforcement, centroidal tension reinforcement, and especially this dt value. These are much larger strains. So uh, if you wanted to incorporate, you will have to incorporate another T force over here at the level of compression reinforcement. You know, this compression T force, and then this is a much bigger T force, you know, uh, much bigger because we have much bigger area 2 number 7 bars. Anyways, so we have so we will be having two T forces and a CC force acting you know, at half of A by 2. That would be like very close to the compression uh, surface, top compression surface at A by 2. So I mean, this is something, this will have a negligible contribution. This ASFY had a lever arm of D minus A by 2. This lever arm was what we calculated actually. This was, you know, D minus A by 2. So we incorporated this over here, ASFY into D minus A by 2. If you want to consider the contribution from compression reinforcement, we neglected, I'm telling you we neglected, but I just want to show you, if you wanted to consider, how would that, how big a difference is that going to be. So this is the lever arm for the compression reinforcement. Now this lever arm is, you know, this total distance was D prime, 2.5 inches, and if you subtract half of you know, this distance is A by 2, at which CC is acting, this is A by 2, and so from D prime you will subtract A by 2. So just as you subtracted, you had D minus A by 2, you will have another term D minus A by 2. So if I wanted to consider the effect of compression reinforcement, then Mn would have been equal to, I'm writing it in black because this is not, there's something you need to do. Mn would have been equal to ASFY into D minus A by 2. In all cases, we are taking the level of CC as moment center, plus AS prime. In this case, Fs prime is also equal to Fy, because compression steel, this is you know, greater than all the so-called compression steel. We are adding we are adding this prime because it is a so-called compression reinforcement into its lever arm, D prime minus A by 2. Now this lever arm is a very small value, and this is the only reason we can neglect it. You know, this answer we have already calculated. This was, I think, equal to you know, in kip inch, this was 4340 kip inch, and if you consider this second term, this answer would have been equal to you know, we have two bars of number 8 in this region. These are two number 8 bars. Their area was 1.58 inch square. So let me show you how would this contribution look like. 1.58 inch square into 60 ksi is the yield strength, and then D prime is 2.5 inch minus A by 2 is 0. Let me check. This A value is 0.78 divided by 2. So you are getting this, you know, this will remain 4340, and this will become, let me calculate. So this answer is 200 kip inch. Now let's see how it looks like in kip feet. So let's do it in kip feet. This answer was 362 kip feet from the real tension reinforcement, and this would become, if you divide this by 12, you get 16.6 kip feet. Now, you know, this 16.6 kip feet is not a big value compared to this. This is, you know, a small percentage of this 362. So if you see, this is just, a small value, just, just a 4 or 5% difference. So that's why the smaller value it can be neglected. And this is, I mean, sort of an extreme case where a value is very, very small. A is 0.72 inch. If this value were a bit higher, we would have even smaller. I mean, if this is 0.78. For example, if in another case, this value, let's say it becomes 2 inches. If this a value is 2 inches, you will be like, this will be 2.5 minus 2 by 2, making 1.5. So the lever arm would be even smaller. So in that case, this moment will be even smaller, and it will be rather more reasonable to neglect this value. So this is the reason we did not include it in this answer for Mn. So the best way to demonstrate that you can neglect something is to actually consider it. I mean, consider it and calculate the final value based on considering it, and then show that this is so small compared to this, and it's not going to make a big difference, so you can actually neglect it. So we have neglected this. And one last thing, that although we haven't been explicitly asked to do, but we must, it's a good practice to do this. So check the AS minimum check. So check AS is greater than or at least equal to AS minimum. Check this. So again, the formula for AS minimum, you know, we can import it straight away from here, and we will use it right here. So this is the AS minimum formula. I mean, it's the larger of these two values, and we have discussed about this BW. This BW would be, this is a case of, I'm sorry, I put it in the wrong place. I'm sorry. I was supposed to place it here. Yeah, this is the AS minimum. These are the main AS minimum expressions. So larger of these two has to be taken. We have discussed this BW when we were discussing that AS minimum in flange sections. We discussed that BW will be taken equal to the given BW, except in this case when flange is in tension and beam is statically determinate. Now in our case, the beam is first of all, the beam is statically indeterminate because it's a part of this of a continuous floor system, continuous on this side, continuous on this side. So naturally it's a continuous beam, so it is an indeterminate beam, so that exception doesn't apply. Even in this case, even in this case, this one situation that this is a statically indeterminate beam, only this information is sufficient to conclude that you have to use actual BW over here, 12 inch over here. But just to comment on it, the other requirement for this exception, for applying this exception, was that flange should be in tension. In this case, flange is in compression. This flange is in compression. So neither of those exceptions, neither of those two conditions exist over here. Even if one of those does not exist, so you don't have to worry about BW. Straight away BW is equal to 12 inch. So in this case, let's try to calculate. AS minimum would be equal to 3 under root of this 4000 psi over 60. BW is 12, D is 20.5, and for the other case we have 200 over 60 into 12 into 20.5. So we need to see the answer for this. If this answer is greater than 200, we will calculate it based on this. Let's calculate this. So this answer is 3 under root of 4000. This answer becomes 189, or should I say 190. So this answer is 190, and this is 200. So naturally the second one, this one will govern. So we will calculate only the second one, and this answer is 0.82 inch square. So our AS provided is our AS provided was 0.36 inch square, and sorry, not 0.36. Let me check. sorry, this is not 0.36, this is 3.6. I mistakenly wrote over here 6 into 0.6 was 3.6. I mistakenly took it 0.36 to 0.36. The rest of the calculations are same because I've just copied from the book. The answers are copied from the book. I haven't calculated them myself. Most of the answers are copied from the book. So the rest of the calculations are, I think, quite good, but just a mistake over here in writing this answer. So AS is 3.6, and I've made the correction with the different color, so you can later on see that this has been corrected. Our AS provided is 3.6. So AS is 3.6 inch square, and this is greater than AS minimum, which is 0.82 inch square. So this is okay. Now we have done the first part. Now let's go to the second part. In the second part, let me help you recall what was the given problem. The given problem was we were given this continuous part of the continuous floor system, and we were asked to determine for this floor beam, we were asked to determine the phi mn at this section AA. For this section AA, we were required to determine phi mn, and then for this BB section, which is the negative bending moment section, we were required to determine phi mn. So we have done the first part, the section AA, and now we are going to discuss the section BB. So this is our section BB, and let me see what is the other data given for this beam. For this beam, so FC prime and Fy are the same for this beam as well, but what has changed? We have different, this beam is, this section is subjected to negative bending moment, which means hogging, and that means tension at the top, compression at the bottom. Tension at the top, compression at the bottom. So now this is the compression zone, and this is the tension zone. So, flexural cracking will start appearing on this side. So, AS this time is, at the top. AS is this time at the top. Tension steel is at the top because it's the negative bending moment region. Just make sure you don't straight away by looking at this and you start writing it as AS 3 number 7 bar. This is this time AS prime. This is the compression side. Let me write it that this is the compression side, compression phase, and the other side is the tension phase. So this phase is the tension phase. So now what you observe in this case is that the tensile steel area is, we have some bars over here, 3 number 8 bars over here, and then 3 number 5 bars each on the left and right side. This is because ACI requires that some portion of the tension reinforcement should be provided, should be distributed into the flanges. So not all the tension reinforcement should be concentrated in this web region. Some reinforcement needs to be distributed in the flanges region. So there are some guidelines regarding how to distribute this, but I'm not going into those details right now. So just I want to point out that you need to include these 3 number 5 bars on each side while you are calculating the AS. So include them in the tension reinforcement. So AS is equal to, you can see 3 number 8 bars. So AS becomes 3 number 8 bars, so 3 to 0.79 inch square, and total 6 number 5 bars, so 6 into 0.31 inch square, 4.23 inch square is the total AS. And we also have AS prime over here, 3 number 7 bars. So AS prime will be 3 number 7 bars. So 3 into 0.6 inch square equal to 1.80 inch square. So we have AS and AS prime. Next we need to figure out D and DT as well as D prime. So using the assumptions or considerations that we have already discussed, these values can be easily tabulated. In this case, D is distance from this compression phase up to the centroid of this tension steel. So again, you can take it equal to 24 total depth minus this distance. This is 2 point, this can be taken equal to 2.5 inch again. So you can simply write in this case that D is equal to 24 minus 2.5 equal to 21.5 inch, and dt, because this tension reinforcement this time is in single layer, so d and dt are same, so d is equal to d, dt is this time equal to d, which is 21.5 inch. So d and dt are now known, and d prime would be equal to distance from this extreme compression fiber to the centroid of the compression reinforcement, and again you can take it equal to 2.5 inches. So d prime is equal to 2.5 inch. Now the main thing that you need to note in this case is that you see in this case the flange is in tension and compression zone is on this side, on the bottom side. So naturally the compression zone is a rectangular section. So for example, if this is the depth of neutral axis, so this compression side will be naturally a rectangular compression zone, so constant width compression zone. So this time this is very similar to a rectangular beam analysis, with the difference that now you have reinforcement both on the tension and compression side. For case 2, we usually cannot neglect the presence of compression steel, so we will be considering this as a doubly reinforced section because we have some sufficient compression reinforcement and we expect some sufficient lever arm for this compression reinforcement. So we need to apply the procedure that we learned for doubly reinforced sections. So you need to, just go revise 4-7, article 4-7, and you can easily solve it. So this was the procedure that we discussed for doubly reinforced sections. You start with the assumption that tension steel is yielding, then you select a value for C, and based on that selected value you calculate epsilon s prime, fs prime, and making sure that the value you take is lesser than Fy, and then you calculate Cs prime, force in the compression reinforcement, then you calculate Cc, compression force contributed by concrete, and then you can calculate T value, and then just check your equilibrium. If T is equal to Cc plus Cs approximately, then you can go ahead and calculate your epsilon s and make sure your assumption at step number 1 is correct, and then you can calculate Mn. If you come to know that this equilibrium is not satisfied and T is greater than Cc plus Cs, and then you increase C and come up with a new loop. So again you continue until the equilibrium is satisfied. If T value was lesser than the right hand side, you could decrease C and come up with again with the same procedural calculation. So you will be using this procedure right here also, because this is also a compression, a doubly reinforced section. So let's start with the calculations. The first step, as we see, was to assume that epsilon s is equal to or greater than epsilon y. So let's assume that epsilon s is equal to or greater than y. So assume epsilon s is equal to or greater than epsilon y. So next you select a trial value of C. The general starting guidelines are that you should start with a value of C between d by 3 and d by 4. Let's take a value of d by 4. So we have taken some value of C close to d by 4, some 5.5 value, and next step is calculate epsilon s prime based on this formula, put the values, so you get this answer. Next you calculate fs prime based on this formula and making sure that you do not take the value greater than Fy. So putting these values you get 47.5, this is lesser than 60 ksi, so this is fine. If this value had exceeded, Fy would have taken it equal to Fy. So this is fs prime. Now you can calculate CS in compression force contributed by steel. So CS would be simply equal to AS prime into, if you remember this, we will have to take fs prime minus 0.85 fc prime because of what we have already discussed. So you can then put the values. So as prime is 1.80 inch square fs prime, and then you put the value for fc prime and get your answer 79.3 kips. So you have now cs calculated. Next you will calculate cc, which is 0.85 fc prime bw into beta 1c. Make sure you use bw over here because compression zone has a constant width of bw this time, so make sure you use bw over here. So this cc will be equal to again putting the values, so you get 191 kips. So you next calculate t value ASFY, and just putting the values you get 254 kips. So we have moved up to the 7th step of calculating T. So now we have these 3 forces calculated, and now we are going to perform this equilibrium check. So let's see. T is 254, and this CS plus CC is equal to this 79.3 and 191. So these make 270.3. Now T value is lesser than CS plus CC. So T is lesser than CS plus CC. So what should you do in the next step? You need to, this side is greater than T. So you need to try a smaller value for C. You need to try a smaller value for C. So maybe we can try C equal to 5.1 inch. And based on this, we can just write down the same calculations that we had done. So you may perform it on Excel sheet, and this will be really quick. So epsilon S prime for this case becomes 0.00153, and then next we calculate Fs prime based on this, and that becomes 44.4 ksi, again less than your 60 ksi Fy, and so this is your Fs prime. And then you calculate your CS, which is 73.7 kips, and then you calculate again your CC, which is 177 kips. 177 kips, and then you calculate your T value again, which is same answer, 254 kips. So this time again you can check their sum is equal to, if you sum them up, they give you 251. Their sum is 251, this is 254, so this is now close enough. If you are using Excel sheet, you can try another value for C, slightly greater than this, slightly greater than 5.1. You will be getting, maybe you can try 5.15 or so. I'm not sure about the actual value, but this is still manually calculating. This is still a good result. 251 and 254 approximately equal. So we can stop the iterations here, and now we can just go ahead. What are the next steps that we need to consider? Once this answer is yes, you can calculate epsilon s and check your assumption, this assumption. So you need to calculate epsilon s next based on the last value of C. So epsilon s would be equal to d minus C over C into epsilon cu. So your answer for this will be 21.5 minus C, the last value that we tried was 5.1. So this gives you 0.00965, and this is certainly epsilon s is certainly greater than epsilon y, which is 0.00207. So your assumption, this assumption is correct. Now if this assumption is correct, you can go ahead and calculate your mn. So But again, before we go to Mn, in this case, dt is equal to d. So when you calculate epsilon t, it will be equal to epsilon s. So this value is 0.00965 as already calculated, and this is greater than 0.005. So phi value can be written right here equal to 0.9. This is a tension control section. So we have it phi value in advance. So next we just need to calculate our mn value. So mn would be equal to so next we will calculate mn, and this is how you calculate mn. So just write down the formula over here. So we can just put the values, but of course so far we haven't calculated a. So this a value can be calculated from c. A is beta 1 c, and beta 1 for fc prime equal to 4000 psi is 0.85. So you can calculate a equal to 4.3 over here. So now just put the values and get your answer for mn, and this answer becomes equal to 4820. No, sorry. Yeah, the final answer is 4820 kip inch, and in kip feet we can write 401 kip feet. So phi mn would become 0.9 into 401. So this will become 361 kip feet. So this is the answer for phi mn. Again, most of the things are still the same as the previous part, except that we have a different d this time, 21.5 instead of 20.5. And the only thing again that I want you to remind is that as we discussed in our general discussion, we take BW equal to the width, web width, except in this situation when flange is in tension and beam is statically determinate. Now in our case, although flange is in tension, that's right, but the beam is not statically determinate. The beam is statically indeterminate. It is continuous. You see, it is continuous over over these girders. So naturally, this is an indeterminate beam. So again, we will still use BW equal to BW equal to 12 inch. So BW will be equal to 12. That exception does not apply. That exception does not apply even over here, because beam is statically indeterminate. So we can calculate this, and now of course this value will be slightly different. You will be getting a different answer. This will become 0.86. So let me correct this. This will become 0.86. So this is the only change that you will see. Again, our AS value is a good sufficient value. Our AS is 4.23 inch, and that is greater than AS minimum. So AS is greater than AS minimum. Okay. Next we look at a quick example for a beam in which the neutral axis would be lying in the web. So this is the given beam, and these are the dimensions at image. This is an isolated T-beam. Make sure you don't confuse it with the T-beam, which is a part of a continuous floor system. This is an isolated T-beam, and we have two layers of tension reinforcement, two layers of reinforcement over here. Now this is the given cross section, and very important to note is you have been asked to compute positive moment strength. What does it mean? If this section is subject to positive moment, what will be its strength? What will be its phi mn value? And also compute AS minimum. If it is subjected to positive moment strength, the first thing that you need to note down is it will be subjected to sagging, which means this bottom side will be subjected to tension, and this the top side will have compression. So if you are just for the sake of discussion, if you are given this section and you are asked to determine the negative moment strength, then this beam would behave as if it was not even reinforced, because under negative moment this would be the tension zone, and there is no reinforcement shown over here. So that would be like free to crack, and that would be like unreinforced beam. so that would abruptly fail, just like a plain concrete beam. So very important to note, we have been asked to determine positive moment strength, so only then this will become the tension zone, and this reinforcement will act as tension reinforcement. And I want to remind you, this is R, and this is an isolated T-beam. Now, the first thing that you need to check is the dimension requirements of ACI regarding the thickness of flange and BE. Now, in this case, you can see that BW is equal to BW is 10 inch, and the other values have also been given. The H value is 28 inch. Just list down some of these values. H is 28 inch. You don't need this in your calculation, I guess, but just write down the data. D is 24.5 inch. And what else has been given? Yeah, you have been given thickness of the flange, which is, HF equal to, let me just quickly see it again, 5 inch again, 5 inch. So 5 inch has been given. Now AS is, let me write down all the data first. AS is 6 number 8 bars, so this becomes 4.74 inch square, 4.74 inch square, and AS prime is in this case 0. Now BE, which is the actual, now in this case this is dimension is 18 inch, and we now are going to check the ACI requirements for this isolated T-beam. For isolated T-beam, we had studied that let me show you those notes. These were the requirements of isolated T-beam ACI requirements. Flange thickness should be this flange thickness, should be at least equal to or greater than half BW, should be at least half BW, and BE is equal to actual width not exceeding 4 BW. So these two requirements we are going to check over here. Now in this case, flange thickness is 5, and this needs to be equal to or greater than half of BW, which is 10. So this is okay. These are just equal, so this is okay. This is okay. And BE is equal to the actual width 18 inch. The actual width is 18 inch, but the limit on this is 4 BW. Upper limit is 4 BW, should be equal to or lesser than 4 times BW is 10. So this is equal to 18 inch actual dimension. All right. So we have checked the ACI requirements. It meets the ACI requirements. Fine. Next, you need to consider that in this case the compression is on the flange side. So there are two possibilities. One possibility is that the A value would be lesser than HF. So the equivalent rectangular stress block will be completely within the flange, which would be case number 1. And the other case would be that the other possibility is that A value is greater than HF. In that case, the equivalent rectangular stress block will extend down into the web, and in that case you will have to perform a different analysis. You will have to consider that the compression zone would be a T-shaped zone, and you need to make some artificial divisions within the beam. So let's see which case is this. First of all, we will assume that this is case 1. So let's assume that this is case 1. So we assume that this is case 1, and that means we are assuming that A would be equal to or lesser than HF. And then next we assume that epsilon S is equal to or greater than epsilon Y. And then third, we are going to calculate A value based on our assumption that tension steel is yielding. So that would be ASFY divided by 0.85 FC prime BE. All right. So let's put the values. So we have just put the known values. Make sure that you take care of this B. This is BE based on the assumption that A is equal to or lesser than HF, which means the rectangular, the compression zone will be a rectangular compression zone with width equal to BE. So we get an answer for A, which is 6.20 inch. Now this A value is 6.20 and HF is 5 inch. So this A is greater than HF, which contradicts this assumption. So you need to, in fact, you need to go to case number 2, because this is no more valid. So if this is not valid, you have to go to case number 2. So we will use the case 2 procedure for which A is equal to or greater than HF. So in this case, we will break the actual cross section into two parts, one having this overhanging flanges and the other having only this web part. So we will calculate CCF and CCW based on these equations. We have discussed them. So now we are going to just use these expressions, and based on this we will be calculating this A value from this equilibrium equation, and then C value based on this, and then epsilon S value based on this C value, and then we will confirm our assumption and finally calculate Mn. And since we don't have any compression reinforcement, so we don't need to consider the later equations, we just have to be here, just end over here. So this is simple process. Again, we're just executing this. So we need to divide the cross section into two parts, overhanging flanges and the web part. So we have divided beam into two parts. One is called beam F and the other is called beam W. F because we are considering only overhanging flanges in this case, and this we have called beam W because we are considering only the web in this case. So let's proceed with the calculations. So this is how you can calculate CCF. We have discussed this formula and just we have put the values over here. BE is 18 inch, BW is 10 inch, FC prime was 3 KSI and HF was 5 inch. So this is the answer for CCF. So CCW is given by this expression 0.85 FC prime BW into A. We can put the value of FC prime 3 KSI, BW is 10 inch, but A is not yet known. So this is an unknown in this equation. So we can write down the expression in terms of A. Okay, so next we can calculate T value. So T would be given by, T would be given by, based on our assumption that the tension steel is yielding, whereas we are retaining that assumption, and so T can be calculated as ASFY 4.74 inch square into 60 KSI. So T value becomes 284 kips. Now you can set up the equilibrium equation that T has to be equal to this CCF plus CCW, and then you can just put the values. 284 equal to 284 kips equal to CCF was 102 kips, all right, and then this CCW is in terms of A, so 0.85 into 3 KSI into 10 inch into this A. So now you can solve this expression for A and get your answer for A. So this way A will become a known value, and if you solve this for A, you get 7.15 inch. 7.15 inch. So now, of course, this value, as we had come to know already, this A value is greater than HF. This confirms that there's a case 2 analysis. So next you can calculate your C value based on this. So C would be A over beta 1, so 7.15 over 0.85. This becomes equal to 8.42. In this case, FC prime is 3000 psi, and for that range up to 4000 psi, beta 1 remains equal to 0.85. So C is 8.42 inch. Next, you can calculate epsilon s, d minus c divided by c into epsilon cu equal to, d is 24.5 minus c is 8.42 divided by 8.42 into 0.003. So you can get the answer over here, 0.00573. So this clearly exceeds epsilon y, which is 0.00207. So our assumption that tension steel is yielding, we had assumed over here that tension steel is yielding, so we had put Fs equal to Fy, so that assumption is correct. And as far as epsilon t is concerned, in this case, since epsilon it is equal to epsilon s because dt is equal to d, this is single layer, no, I'm sorry, we don't have a single layer reinforcement, so epsilon t would be for epsilon t, since dt is greater than d, so epsilon t would be definitely greater than epsilon s, and even epsilon s is greater than 0.005, so epsilon t would be definitely greater than so epsilon s, even epsilon s is greater than 0.005, so epsilon t will be definitely greater than epsilon than 0.005, so phi value is 0.9. And the last step now is to calculate mn value. So you can now calculate mn based on what we have already discussed. So mn would be equal to, CCF into its lever arm d minus HF by 2, and then you have the contribution from CCW, which is d minus a by 2. So the CCF force was equal to 102 kips. So 102 kips into d value is 24.5 inch minus HF is 5 inch by 2 plus CCW value is 182 kips, multiplied by again 24.5 inch minus 5 inch. Sorry, this is not 5 inch, this A value was, we had calculated A value to be 7.15, so minus 7.15 divided by 2. So you get the value for Mn. So this phi Mn can calculate, after you calculate Mn, you can calculate your phi Mn. So lastly, you need to check again that AS is equal to or greater than AS minimum. So same expression for AS minimum. Now AS minimum is given by larger of these two, and we have discussed that as far as this BW value is concerned, there is only one exception. That exception is when flange is in tension and beam is statically determinate, then BW is replaced by larger of 2 BW and BE. In our case, flange is in compression. So flange is in compression, and maybe the beam is also not determinate. We are not given any information regarding whether the beam is determinate or indeterminate, but we surely know that the flange is in compression. So if flange is in compression, then this exception does not apply. So when flange is in compression, we can simply use BW equal to whatever the given value is. So again, 3 into this 3000 divided by 60 into BW into D. BW in this case is equal to this 10 inch. So you can just put the value over here. D value is 24.5 and again you can compare over here these values 200 over Fy into 10 into 24.5. So again you need to see whether this value is greater than 200 or smaller than 200. So often this value will be again smaller than 200. This value comes out to be 164. So this value is lesser. Of course this value is going to govern. So we will calculate only the later value. So that becomes 200 over this Fy is 60. I just didn't put the value, but this is 60. So you get the answer equal to 0.82 inch square, and our A is provided is much larger than that. So our A is provided is 4.74. So AS provided is greater than AS minimum. So that's okay. So this is the end of this lecture. So now you are going to have a surprise quiz. You are going to have a surprise quiz. Please open the link provided in the description of this video and enter your registration number, and also give the right answer. This is not a multiple choice question. You have to write the answer, maybe a one-word answer, but you have to write it. So I'm giving you some time so you can go and open the link. I want you to keep it open right from the start of the video, but if you haven't opened by now, please go and open the link. Alright, I'm assuming that by now you have opened the link, and here is some situation that the question is not yet appearing because I want you to first see the problem statement and then I'll show you the question. This is an inverted isolated T-beam. This is an isolated beam, not a part of continuous floor beam system. It is an isolated T-beam. This is an inverted one. I mean, this is inverted T-beam. It is subjected to positive bending moment. It is subjected to positive bending moment. Now the question is, what will be the shape of the compression zone? What will be the shape of the compression zone? Go ahead, answer. Maybe a single word answer will do, but yeah, make sure you give the answer. So I hope you have submitted your answer along with your registration number, and this is the end of this video. Thank you very much. But here is an assignment for you. These are the problems given at the end of this chapter in the James K. White book. So we have 4-1, and then we have up to problem 4-12. We have we have 12 problems in this exercise. If you are an odd registration number, solve all the odd number problems. I mean 4-1, 4-3, 4-5, and so on. All odd numbered problems. If you are an even registration number, solve all the even number problems. I mean 4-2, 4-4, 4-6, 4-8, and so on. So you have to submit this assignment within the next week. We have 1 week to complete this assignment. Please go ahead and submit this assignment by this is today. This is 26th July when I'm recording this. So you will be watching this on 27th July, and on 3rd July, yes, you will have your deadline. But okay, because of Eid, I'm extending the deadline all the way up to 7th July. 7th August. 7th August is your deadline for submitting this assignment. 7th August. This is the end of this video now.